Welcome to this biochemistry lecture on amino acid ionization. So the net charge on an amino acid depends on the pH of the solution. An amino acid is a Zwitter ion, meaning it has different functional groups that can be positively and negatively charged, and thus it is commonly found at different charge states, including a net no charge. So, and again, that's totally dependent on the pH of the solution. So if we dissolve an amino acid in water, the aqueous environment that we have will cause different functional groups to be charged. And so let's say if we take this amino acid and we put it into an acid solution, a low pH solution, the carboxyl group, the solution will donate a hydrogen to the carboxyl group, and you'll end up with a net positive charge. The isoelectric point of an amino acid, or commonly referred to as the pI, is the pH at which the amino acid has no net charge. Commonly, what you're going to find at acidic pH, the carboxyl group is protonated, and at a neutral pH, the carboxyl group is deprotonated, but the amino group is protonated, and so you have a net zero charge. And then when you have a low pH, an alkaline pH, the amino group is neutral, and the amino acid in the carboxyl group is negative, and so you get a net negative at lower pH. And here are the common isoelectric points for these amino acids, and you can see that generally they are found between 5.5 and 6, generally around 6. Except for the acidic and basic, the 5 amino acids that are either positively charged or negatively charged, which have very different pIs. Again, the pI is the isoelectric point, and that's the pH at which the majority of the molecules in the compound have no net charge. This chart kind of gives you an idea of kind of how that works. As the pH goes up from 0, or from 1 or 0, you're going to see less and less of the form that's shown in the pink box, the red box, and you're going to see more and more of the Zwitter ionic form, which has a net neutral, has no net total no charge. You'll see more and more in the blue. As we get into the alkaline pHs, that form decreases, and we see more of the negatively charged, where the carboxyl group is deprotonated, and therefore you see a net negative charge. And so as we go through the pH range, different forms of the molecule, different charge states of the molecule emerge in different concentrations. So if we're going to do a titration of an amino acid to kind of see where this is, we'll see this. You can see the different forms. So this is glycine. So on the far left, we have the protonated amine group and the protonated carboxyl group. As we increase the pH of the solution, you're going to find the pI is where we have no net charge on the molecule, as the carboxyl is deprotonated. And then as we go into the higher pHs, the amine group gets deprotonated, and so we get a negative charge. And the pKa shows the strength. We'll discuss this in later videos or in different videos, but the pKa is how strong the acid is, and the pKa tells you how there's a direct relationship between the pKa and the pI. Again, the pI is the pH at which the molecule has a net zero charge. This gives you an idea what pH you're going to find the charge states at. So here is the formula for the pI as it relates to the pKa. So we can empirically determine what the pKa is of each state, and therefore we can calculate the pI of each amino acid. There are some amino acids, like histidine, all the charged amino acids, like histidine, that have a relationship to, so histidine is a net positive charge, and so the pI is still an average of 2 pKa's. In this situation, you take the pK2 and the pKr, and you average those two, and that will give you the value of the PI. In the case of glutamic acid or others, you take the pK1 because it's a negatively charged ion, and that's how you, in this situation, calculate it. It's a lot more complicated than that, but that's well beyond the scope of what we're trying to do here. Again, the important part is we could calculate the PI by knowing the pKa and averaging the pKa values in the equation that was shown in the last slide. Again, histidine is a classic example. Histidine has 4 ionization states where it becomes more or less deprotonated and has a very unique PI, and where as do the other 3, or the other 4, I guess I should say, other 4 charged amino acid residues. This gives a pretty straightforward example of what to do. This type of equation, this type of calculation is very important to know as you go forward in biochemistry. We look forward to seeing you in the next video.